then it will not follow the straight path, it will bend. Okay. Now it found that whenever the charge particle bends, the velocity of the charge particle is not going to be changed. Okay, velocity remains same. Okay, throughout the path, the velocity will not change. That means the kinetic energy of the charge particle is constant. Okay, so this is the third observation. First observation was if the particle is at rest, it remains at rest. If the particle is moving, then it will move, but it will deviate its path. So it will some kind of bending takes place, the deviation takes place. And in the third part, he observed that if the particle is moving and there is no change in the velocity, so it remains same. As speed is remaining same, that means the kinetic energy of the particle is found to be constant. Okay, this is the observation, that's how we study. Now, the charge particle deviates means there must be some kind of force. Okay, so if there is no force is acting on the charge particle, that means there is no deviation. So since the charge particle deviates, that means what you can understand that there must be some kind of deviation. Deviation is there means some kind of force is acting on it. Okay, some kind of force is acting. Now this force acting on the charge particle must be perpendicular to it. Why? So let us say this is the force acting on this direction. The force is perpendicular to this particle. Why? Because the force has to be perpendicular. Why? If the particle is moving at certain speed, if the force is some angular direction, let us say there is a particle of mass m and the particle is moving with some velocity v. If we apply a force in this direction, then the component of v has to be increased. Okay. So v remains same only when the particle is moving with v and if we apply a force which is perpendicular to this. Okay. Then only the v remains constant. So this is the fourth observation that there must be some kind of force acting on the particle. Okay, there must be some kind of force. Now, since this force is not electrostatic in nature, why it is not electrostatic? Because if the force is electrostatic in nature, then the charge will deviate or it will deflect whenever it is at rest. Okay, so the charge particle shows some kind of deflection. Why the deflection takes place? On further analysis, it has been found that there must be some force acting on this charge particle, then only there must be some kind of deviation. Okay. Now he found that since the velocity remains constant, the particle is not moving at variable speed, the particle is moving continuously with constant speed. That means there must be some kind of force which should be acting on the perpendicular direction. Okay, this is the fourth observation. And next observation is that if the force is there, that means that particular force cannot be electrostatic in nature. Why? If the force is electrostatic in nature, that means there must be the deviation when the charge particle is at rest. Okay, so that means that force, fifth observation is that force is not electrostatic in nature. Force is not electrostatic in nature. Okay, now what is the nature of the force? Now, in order to identify that, he put a magnetic compass, magnetic needle. So he bring a magnetic needle. So what is magnetic needle? Magnetic needle is a round shaped object where the magnet is being placed. So let us say this is the magnet. Okay. Now this arrowhead is colored with red. Now red color signifies that this arrowhead is visiting the north pole of the pole. Okay. Now once he places this arrow magnet or the compass in that particular position, and if he move the compass, and he found that the deflection of the needle is along the same direction as that of the deflection of the charge particle. Okay. So the path in which the charge particle shows the deflection is the same arrowhead along which the compass needle also deflects. That means that particular force which is deflecting the compass needle, which is itself a magnet, that means that particular force is a magnetic force. Okay. So final observation is that the force is F is Fm. What is Fm? Fm is the magnetic force. That means what is the final conclusion? Final conclusion is that whenever the current carrying wire is there, then there is a deflection shown by a magnetic needle. Why? Because there must be some kind of force acting on it. That force is the magnetic force. Okay. Now, once I found this force, next the question comes, why this force comes? Why this force comes? Now, answer to this question is that instead of producing the force first, the current carrying wire is producing a field. Okay. as we discussed about the electric field, there also another type of field is being produced, that is known as the magnetic field. The seventh observation is, so magnetic field is being produced. Why? Because the force is magnetic in nature, so field is magnetic field. Field is magnetic field. So there is a magnetic produced because of the current carrying. Understood? So these are the observations made by the experiment carried away by Henry Wested in the year 1820. Okay, so first of all, under the electromagnetism chapter, we have to learn about this experiment, how this experiment takes place, and what are the observations. So this is the basic idea of the experiment. Now, whenever I am saying there is a moving charge, so charge having some kind of velocity means there is a moving charge. Okay, so moving charge will feel the force. If the charge is placed, then there will be no force. And in place of moving charge, if I place the magnetic needle, will also feel the force. Same variety of force is being felt. Okay, so that's why the name of the force is given to as the magnetic force, and correspondingly, the field has to be identified as the magnetic field. Okay, now come to the experiment that has been carried away by the Wested. So in this particular setup, so this is the switch. This is the switch. If I close it, then the current will flow. And this is the battery. Let us say this is the positive side, this is the negative side, this is the battery, and this is the resistance box rheostat. Okay, variable resistance. So once I switch on the circuit, then the current will flow in this direction through the wire, to the AB where the current is flowing in this direction. Okay. Now below of it, I am placing the magnetic needle. You can see that this is the red part, this is the north pole of the magnetic needle placed just below the wire. Once I switch on the current or switch on the circuit, then the current will flow, and ultimately what you can saw that there is a deflection of the magnetic needle along this arrowhead direction. Okay, there is a deflection of the magnetic needle along the arrowhead direction. Why this deflection takes place? Because as we know that this is current carrying wire, let us say the I amount of current is being produced supplied. Now this I amount of current is going to produce some kind of magnetic field, and that magnetic field creates some kind of force which is known to as the magnetic force, and because of that magnetic force, the north pole has been deflected. Got it? Now the question comes, in which direction the magnetic needle will go. So for that I have to follow one particular rule. What is that rule? Now that rule is known as the right hand thumb. Okay, so you use the right hand thumb rule to find out what is the direction of the force or the field along which the north pole will deflect. Okay, if you place the right hand thumb, place the right hand thumb along the current carrying direction and fold your finger. Place the right hand toward the current carrying direction. That means in this particular situation, you place your thumb along the left hand side. Okay, and once you fold your finger and allow the finger to pass below the wire. If you place below the wire, then the finger tendency will be towards yourself. The tip of the finger will be pointed towards yourself. That means in that direction, the north pole will be. Understood? So if I place the right hand of our thumb along the left hand direction, and if I fold my finger, so fingers will be folded, and if I allow the fingers to pass below the wire, if you feel that, you can feel that the fingers are pointed towards ourselves, towards myself. That means this will give the direction in which the north pole will deflect. Okay, so north pole will deflect towards ourselves. That means towards the out of plane situation. Okay, so this is the observation that has been made. Now, not only that, we perform a lot of experiments on this particular setup. What are the experiments? So these are the different setups. Okay, so in this particular setup, you have to understand some of the nomenclature. Now, what is the nomenclature? So this is the basic circuit that has been given to you. Now, if I put a dotted line, so this dotted line is representing the compass. So if the line is mentioned with dotted line, that means the compass is placed below the wire. Okay, below the wire means, let us say this is the wire through which the current is being flowing, and I place the wire compass below of it. Okay, the symbol to represent this type of diagram is, use the dotted line to represent the compass and put arrowhead like this. Okay, so that will symbolize the compass. If I place the compass top of the wire, okay, let us say current is flowing in this direction, I put the compass in above the wire. Then you have to put a firm line for the compass and draw the arrowhead. Okay, so these are the two notations that we are going to use to represent the location of the compass, where the compass is being placed. The compass may be placed below the wire or it may be placed above the wire. Depending on that, the deflection will be different. And in order to measure the deflection, we use the north-south, east-west rotation. Okay, let us say the current is for the first situation. Once I switch on the battery, and that means the current will flow unless and until key is now here the key is in open position. Key is in open position. That means no current will flow. So I will be zero. No current is flowing. So key is open and compass will be kept below the wire. That means there is no deflection. Okay, why? Because we understand that if the current is not there, that means no amount of magnetic field is being produced. And if no amount of magnetic field is being produced, there is no amount of deflection. So in the first case, what you have learned that the switch is open, E is open situation. That means there is no current is being flowing. So no current is being flowing means it will show no kind of deflection. Now we close the switch. Here the switch is being closed. Now depending on the positive and negative side of the battery, we understand that the current will flow along this direction. Okay, that means now the compass is represented with dotted line. That means it is placed below the wire. Now the current is going from A to B. A to B means towards north. Let us say current is going towards north. Current is going towards north. And compass is placed below the wire. And this arrowhead pointed towards the north itself. So this is the north pole. This is the north pole. Red color portion is the north pole. Now if I place our thumb towards right, and if you fold the finger, if we allow the finger to fold below the wire, then the sense is like that. From below the wire, fingers are pointed towards my screen. Towards my screen, the fingers will be pointed. If you fold your right hand, place the right hand thumb along the right hand direction, the right side, because now the current is towards north, means our thumb should be pointed towards right. And if I fold my right hand fingers, so right hand finger will be folded in this direction, So thumb will be pointed towards the right, and fingers will be folded like this way. And the tendency of the fingers from the below of the wire, if I see, so it will go in this direction. So north pole will be pulled in this direction. Okay, the finger direction will always show the deflection of the north. So since the north pole is deflected towards west, so this is our west direction, west side. So deflection will be along west. Okay, along west, and it will be deflected. So it has been shown like this way. Okay, shown by this way. So fingers pointed towards west. That means it will be deflected towards west. That means that direction will give the direction of the north. Now what about the south pole? The south pole will always be deflected in the opposite direction. If north pole is deflected towards west, then we can conclude that the south pole is deflected towards east. Understood? So this is the method by which you can calculate the direction of the deflection. In which direction the deflection has taken. Now why the deflection comes? That we have already said that because of the formation of the magnetic field, and that magnetic field creates the magnetic field. So notation for the magnetic field that we are going to use the P. Okay, similarly, once we go for the electricity current chapter, so there we understand the electric field written by the E vector symbol. Here is the symbol B vector to represent the magnetic field. Here B is used to represent the magnetic field. Okay, and this magnetic field is producing the force which is known to as the magnetic force. And because of magnetic force, the magnetic material has been deflected. Okay, because of magnetic force, the magnetic material has been deflected. So for the north pole, you can clearly see that the force is in this direction. Okay, force is in this direction, that means toward the west, and for the south pole, it will be opposite direction toward east. Okay, so from the experiment, you can also conclude that in which direction the force is being applied. Okay, now come to change the situation. Now in the third situation, we reverse the polarity. Now here this is the positive side, here the negative side. Now remember the north, south, east, west direction. So this is the north direction, this is the south direction, this is the west, this is the east. Okay, this is the deflection. Now the current is being flowing in this direction. Current is being flowing in this direction. That means towards south. So current is being flowing towards south. So I is this direction towards south. Okay, and below this we place the magnetic needle like this way, and the point of the magnetic needle is this is the north. Now again you place the finger or thumb of the right hand towards the left hand side, and you fold the finger. Once you fold the finger, then the tendency is that now the fingers are coming out of the plane. Now the fingers are coming out of the plane. So we are folding the finger in this direction, right hand finger. So tendency is that north pole will be shifted outward. So in this direction, north pole will deflect. Then what is that direction? That is towards our east. So this is the direction of the force on which the north pole will be deflected. So that it will be toward the east. Similarly, oppositely, the south pole will be deflected towards west. Okay. So what we see that the situation just reversed. In earlier situation, the north pole is deflected towards west. Now it has been deflected towards east. Why? Because now we change the direction of the current. So what we conclude from this is that if the direction of the current flow is reversed, and compass needle is kept below the wire, then the deflection as shown in the earlier situation will be reversed. Okay. Now we repeat the same experiment by putting the magnetic needle on top of it. Now it is being farm line. So farm line means magnetic needle is placed top of the wire. Okay. Now if I connect this, so now this is the direction of the current flow. So again the current is being flowing from south to north. So this is the direction of the current flow. But the needle is kept above this wire. And needle is kept above the wire. And this portion is marked as the north. Because every time we are going to see the north. Okay. So if I place our thumb towards our right hand side and if you fold the finger, then now the finger will appear to move away from the surface as we fold upward. So from the upward point of view, if I fold my finger, so finger will be pointed like this way. Finger will be folded like this way. So from the upward point of view, because now the needle is placed up the wire, above the wire. So now the fingers will be folded towards ourselves. That means it will be deflected towards our west, towards our east. Okay. So now this force will be in this direction. So this will be flow that means towards our east. So it will be deflected in this direction. Okay. Now if we reverse this situation, so simply changing the polarity, we can reverse this situation. Now it is positive, it is negative. So that means the current is flowing towards our south. Okay. Then the situation is reversed. Okay, that we already observed when you keep the magnetic needle below the wire. Okay, so by placing the at different orientation, what you understand the deflection of the magnetic needle will be different. And why the deflection takes place? Because current carrying wire produces some kind of magnetic field. Okay, will produce some kind of magnetic field, and that magnetic field will produce some kind of magnetic force. And that is the force which is responsible to produce the deflection inside the magnetic field. And regarding the deflection, what you understand that the deflection of the north pole will be deflected along the force, along the FM direction. Okay. Now to find out the FM direction find out, basically I have to place the right hand along the current carrying wire and I have to fold my finger. Okay, every time you have to check with your right hand. So place the right hand thumb along the direction of current and fold the finger. The finger direction will show you the direction of the deflection of the needle, or rather we can say the force on which the north pole is acting. Now similarly, if we say that this force is there, now why this force comes? This force comes due to B force, magnetic field. Now this is the produced by the I. Okay, so this is the first topic of our interest, that I want to check what is the amount of B produced by this I. Okay, so you understand that I can produce current carrying wire can produce magnetic field. Now the question comes, what is the amount of magnetic field that has been produced by a current carrying? That part of study is known as the magnetic field. Okay. So we are now going inside the magnetism chapter, where we want to study now what is the magnitude of the magnetic field. What is the magnitude of the magnetic field produced by the current carrying wire? So now the topic of the heading is magnetic field and the field lines due to the current carrying wire in a straight. Okay. Now, regarding a straight wire, first of all, we discuss about a straight wire which is a finite length. Okay, which is a finite length. So, finite length means what? Let us say there is a length AB. AB of the wire is known. Okay. Now, we want to calculate the magnetic field at this point, P point, which is at a particular distance of, let us say, R from the wires. Okay. Now, why this wire is called the finite? Because from the point P, you can clearly view the point A and you can clearly see the point B. If you see both the point A and B standing from the point P, then it is known as a finite. Let us say P sees the A at an elevation of, let us say, theta 1 angle, and P sees the B at an depression angle of, let us say, theta 2 angle. Let us say theta 2 angle. Okay, so theta 1 and theta 2 are the two angles corresponding to the point A and B measured from point P. Okay, let us say the current is flowing from A to B in this direction. Okay, now first task is to check what is the magnitude of the magnetic field produced by the current carrying wire at point P. So for that I am going to use one particular formula. The derivation of this formula is not so important regarding for this part. We will discuss in later part of the study, that is in the higher classes, class 11 or 12. So right now we are going to introduce your formula only. So you just get the idea how to calculate the magnetic field at point P. So magnetic field at point P written by the suffix Bp is equals to mu naught I by 4 pi d 4 pi r into sine theta 1 plus sine theta 2. Okay. So this is the magnetic field expression. Now what is mu naught? Mu naught is called the permeability. Okay, mu naught is called the permeability. Similar to the situation what we discuss about the permittivity. So in electricity, we discuss about the permittivity. There we use the number epsilon naught. That's called the permittivity of the free space. That means for that we define that how fast the medium is allowing the electric field to propagate. If I place a charge at a particular point, now charge will produce an electric field surrounding it. Now how fast this electric field is propagating? How fast the electric field is propagating through this medium, that is defined as the epsilon naught parameter. And we define this epsilon naught parameter as equals to number is given as 8.85 into 10 to the power minus 12. That is the value of this epsilon naught. Similar to this, for the magnetism, what you understand that you have to define another constant which is known as the permittivity. Permeability. Epsilon naught is the permittivity and mu naught is the permeability. It is known as the permeability. What is permeability? Similar to the situation of the electric field, now the magnetic field is being produced by the current carrying wire. Now how fast the magnetic field is propagating through a particular medium? Let us say here the medium is air. Okay, so how fast the magnetic field is propagating through the air, that is defined by the term permeability. Okay, now what is this number? Mu naught equals to, what is the value? That is equals to 4 pi into 10 to the power minus 7. That is the number. Okay, so you should get the idea that what is mu naught and what is epsilon. So epsilon naught terms is defined for the electricity. Whenever you deal with the electric current, so electricity or charge, we define this. Okay, or for electrostatics. But mu naught is defined for the magnetism. Magnetism part. Later on, we understand that there is one separate chapter which is known as the electromagnetic wave. Okay, what is electromagnetic wave? Example is light. We have already discussed about the light. So light is basically electromagnetic. Okay, light is the electromagnetic. Why it is called electromagnetic wave? Because in that particular light, both the property of epsilon naught and mu naught are there. Okay, both the property of epsilon naught and mu naught are there. That's why it's called electromagnetic. Name suggests that electric property is there and the magnetic property is there. So since both the properties are there, then it is known to as the electromagnetic wave. And for light, you know that the velocity of light is how much? 3 into 10 to the power 8. Okay. So it has been also found that the C number can be obtained by combining this mu naught and epsilon naught. Okay, if you put the mu naught and epsilon naught number values over here and you calculate it, that number comes to as 3 into 10 to the power 8 meter per second. Okay. So this is the idea about the mu naught. So mu naught is basically measuring the property of the medium. What is that medium? That medium is the free space or air. So mu naught is basically defined for the free space, that is for vacuum or for air. Okay, that number is equals to 4 pi into 10. What is I? I is the amount of current flowing through that. Pi is constant. R is that distance. Okay, distance. What is that distance? That is the particular distance measured for the point P from the wire itself. And theta 1, theta 2 at the angle sin theta 1. So this formula has to be used to calculate the magnetic field at any particular point. Let us say I am taking the values. Let us say if theta 1 is, let us say 60 degree. Let us say this is 30 degree. So there is a one point which is the point P at an angle of 60 degree for the A and at an angle of 30 degree for the point B. So simply put the value. So answer will be mu naught I by 2 pi r. Okay, sine 60 means root 3 by 2 plus r. Okay, that will be your answer. Okay, so this will give the magnitude. This will give the magnitude. Why? Because we are dealing with the magnetic field. The magnetic field is a vector quantity. Okay, so now we have to come to your direction. Now for direction, again you have to go to your right hand thumb rule. So place the right hand thumb along the I direction. Place the right hand thumb along the I direction. And if you fold your finger along this, then you can feel that your finger will be pointed towards inside the plane point P. Huh? If you fold my finger by placing the AB along AB, if I place the thumb, and if you fold my finger, then at point P, fingers are entering inside the plane. And that means if I choose the point, another point Q, from where the feeling will be fingers are coming out of the plane. Now, if I rotate my curl my fingers by placing the thumb vertically, so what I can feel that at point P, the fingers are entering inside the plane, and from point Q, they are coming out. So whenever I am getting the feeling that my fingers are entering, so we use the symbol as cross and inserted. So that gives the feeling that it is into the plane of it, into the plane. Okay. And if I put a dot symbol over here, dot means out of the plane. Dot and then inside. Okay, it is out of the plane. So these are the out of plane. So these are the two popular symbols are used to signify the direction. So what is the direction at point P? It is cross. What is the magnitude? Magnitude is already given to you. Okay. So this is the formula that we are going to use for the calculation of the magnetic field by a straight current carrying wire at a point P which is finite. Which is finite wire. Which is finite. Finite wire, what is the meaning of finite wire? That means I can see the point A and B from the point P. Okay, I can see it. Now the next part is the infinite. Let us say now I am going to calculate the same magnetic field for the straight wire, but it is infinite. Infinite. What is the meaning of infinite? Infinite means now the AB wire is extended at a very large distance. Okay. So from the point P, which is at a distance of R, you cannot view the point T, or you cannot see the point B also. Okay. That means what is the angle theta 1 and theta 2? Theta 1 or theta 2 are tending to 90 degrees. Can I say that? If the point B is far below, then the angle will be far more. Okay, theta 2 is more. So tendency of theta 1 should be almost equals to pi by 2 or 90 degrees. Okay, similarly, that is equals to also theta 2. So if I put this angle theta 1 and theta 2 in the earlier expression, so what was the expression? B at point P should be equals to mu naught I by 4 pi d into sine theta 1 plus sine theta 2. That is our basic expression. Okay. Now we simplify this equation by putting theta 1 and theta 2 as 90 degree. So sine 90 plus sine 90 means 1 plus 1. That means it is equals to 2. Okay. So this number becomes 1 plus 1 means 2. So ultimately this mu naught I by 4 pi d multiplied by 2 means equals to mu naught I by 2 pi. Okay. Now this is d. Yeah, this is d. D is the popular distance. So this formula is valid for infinite. Infinite one. Okay, both way infinite. It's called the both way infinite. What is the meaning of both way infinite? Both way infinite means neither you can see the point A nor you can see the point B from the point P. Okay, then this is the expression. Now there may be one situation that is called the semi-infinite. Now for semi-infinite, that means the word says that one end has been seen. Let us say this is the A point. You can see this A point from the point P. Okay, but the other end, that is the B, cannot be seen. Okay. So for this, what we define is theta 1 angle as 90 degree and theta 2 angle is 0 degree. Now, because now I can directly see the point P A, then theta 2 is 0 degree and theta 1 is 90 degree. Now if I put this in the basic expression, it should be equals to mu naught I by 4 pi d into sine 0 means 0 plus sine 90 means 1. So it gives the mu naught I by 4 pi. Okay. So these are the two separate answer that has to be remembered for two different types of wire. One is called the both way infinite and one is called the semi-infinite. Okay. Regarding the direction, if I say our current is flowing in this wire in this direction, I, so place the thumb along the I direction, curl the finger, so at point P it will be cross. If I say I is flowing downward direction, then place the finger downward and fold the finger. The tendency of the finger should be coming out from point P. That means it should be dot. Okay, it should be dot. So if any type of wire is there, let us say this is the any type of wire through the current is flowing. So if I place the thumb along this wire direction and if we fold it, then I can clearly see that on the right hand side of the wire, the magnetic field is crossed. On the left hand side, it becomes dot. Okay. So that means whenever there is a current carrying wire is there, it will divide the both sides into two different types of magnetic. Direction wise different. On one side, if I say cross, on the other side, it should be dot. Always. Okay. So these are the three important formula that you have to remember regarding the magnetic field. So first one is for the magnetic field due to finite wave. Okay, finite wave. Second one is the magnetic field due to infinite. And the third one is the magnetic field due to semi-infinite wave. So mostly 2 and 3 combinations are very popular. Okay. So you can get the feeling that how to calculate the magnetic field. How to calculate the magnetic field. And regarding the direction, I have already informed you how to calculate the direction. Okay. So this is all about the magnetic field calculation for the straight current carrying wire. Now come to the situation where we consider a loop. So now consider if there is a loop. What is the meaning of loop? Loop means a closed coil. Yeah, loop means a closed coil. So loop means closed coil. The cross section of the loop may be circular. If the loop is circular, then you say the circle loop may be square. Yeah, then you call it a square loop, maybe rectangular. Any type of geometry of the loop may be possible. Okay, any type of geometry of the loop may be possible. But regarding the first of all the direction, how to calculate the direction? So for that, let us say I take a circular coil of radius r. Okay, and let us say current is flowing in this direction. Yeah, current is flowing in this direction. Now for that, you have to change the rule somewhat. So now instead of putting your thumb, now putting the fingers, 4 fingers along the direction of the current. So if you fold the fingers along the direction of the current, the thumb will be pointed outward. Now, so imagine that this figure, the circle is drawn on a vertical plane. Every time imagine this circle is drawn on a vertical plane and you fold your finger in front of your eye along the anti-clockwise direction. So once you fold your finger along the anti-clockwise direction, the thumb will be always pointed towards myself. That means it should be pointed outward. So magnetic field will be dot. Okay. If I put dot symbol for the inside part of the loop, then outside part will be always cross. Again, it will separate into two different parts. One is the dot and the other cross. Similarly, if I take, let us say, I took a triangular loop. Okay. And if you allow the current to flow in this direction, now imagine this triangle is drawn in a vertical plane and you fold the finger along the clockwise direction, the thumb will be pointed towards the plane. So into the plane, that means it should be crossed. So once I mark cross inside the loop, that means at each and every point it should be crossed. At each and every point within the loop it should be crossed, and if I move outside, then it should be dot. Okay, so this is the direction in which the magnetic field will exist. Now regarding the magnitude, so for the magnitude only I discuss about the circular loop, not about any loop. Why? Because square loop or rectangular loop, those loops can be found out from the basic expression of the finite. Okay, since we understand the finite wave, if I consider the triangular loop, basically you have to consider 3 finite. Okay, that combination. If I consider square, means 4 finite wave. Okay, pentagon, 5 finite wave, hexagon, 6 finite wave. Like this way you can calculate. But that calculation is not included in your topic or in your syllabus. Rather, you should get the idea that you can do it. Okay, if I apply 1 finite wave problem, then you have to multiply. For a hexagon, I have to repeatedly I have to use for the 6 different. But there must be symmetrical situation. That means every time you don't have to solve. So solving one problem or for one wire, get the entire effect. But you can do it. You can try it to do it. Okay. I will not discuss about that because that is not the scope of the syllabus. What I will do, basically, we will do a discussion regarding the circular. Okay. So this is a circular coil. Now regarding the circular coil, there is another restriction that I can only measure the magnetic field at the center. That is the rule point. Okay. So magnetic field is existing at each and every point inside the coil. Inside the loop, the magnetic field is existing, but I have the theory to measure only the magnetic field at point O. What is that formula? That is BO, B at the center, is equals to mu naught I by 2R. What is R? R is the radius of the circle. Okay, that is the formula. So this is the fourth formula that comes into the picture that you have to do. Okay, so there is a magnetic field due to a circular current carrying coil. Yeah, and we want to calculate the magnetic field at point O. Okay, that is the answer. Now, regarding the coil may be of single turn or maybe a multiple turn. Let us say you take a long wire and you circle several times. Okay, several times. So, the answer for this, if I say at the point 2, I want to measure it, so answer will be different. Right? Because here you have to calculate the number of turns. How many turns are there? Okay. Let us say n, capital N is the number representing number of turns. So simply multiply with n. So B at point 2 should be equal to one single coil is equal to mu naught I by 2r, and it is nothing but the representation of n defined coil. So it should be multiplied by n. So mu naught capital N I by 2. That will be the answer. Okay. So if I use a coil of multiple turns is there, so simply multiply with this number. So more the number of turns, I can increase the magnetic field strength. Okay, using current. So now I want to look into the fact that how to increase the magnetic field, because there are various situations where you are going to apply the magnetic field. Okay, in real life situation, in medical industry, like CT scan or MRI imaging, in all those situations you have to apply some kind of external magnetic. So magnetic field you have to produce it. Okay, you have to produce it. Now first of all, you understand the unit for magnetic field. What is the unit? Unit is defined as the Tesla. Okay, named after the renowned scientist Nikola Tesla. So Tesla is a unit used for the magnetic field design. Okay. Now in order to increase the magnetic field, so what you can do? I can increase this I number or I can increase the N number. Okay. So forget about the reduction in the R number, because if I reduce the loop radius, then the dimension of the loop will be very less. So in some situation that may be also applicable, but initially what you understand that in order to increase the magnetic field, I have to increase the current. Okay, increasing the current. So suppose in a circuit, there is the current is flowing. Suppose you measure a current of 2 amperes. Now you want to measure from increase it from 2 to 5 ampere, 2 to 4 ampere. That means you are going to increase the magnetic field. But increasing electric current is quite difficult. Why? Because in order to increase the electric current, you have to change the battery. You have to change the battery. So that means it is a costly process. Instead of that, what you can do, you can increase the number of turns. Okay, so number of turns more means more is the magnetic field produced. Okay, so B is the magnetic field symbol. Now we know how to calculate the B, and regarding the direction, I have already said that. Now go for one experiment. Okay, let us say I took the same coil and I allow the current to flow through this wire in this direction. Okay, and the current will flow along this loop. Let us say the current is flowing along this direction. Along this loop. Okay, along this direction. So that means what you can see that from this point the current is entering inside the plane, and from this point the current is coming out. So here I can say a dot symbol with a circle, and here I can see there is a cross symbol with cross and circle. Okay, right? Because now from this point A, the current is entering inside the plane of paper, and from point B, the current is leaving out in the plane. And then finally current is leaving out the circuit. Okay, now the circuit is complete. Understood? Now we put this coil and we place this coil on a plane of paper. Okay, and on this plane we put the iron dust. So these are the iron dust. Iron dust are there. Okay, when I switch on the circuit, now the current will flow, but you can see that the iron dust are arranged in a regular fashion. Okay, so these are the different directions in which the iron dust are being oriented. Can I see that? So these are the directions in which the iron dust is oriented itself. So these directions are basically the direction of magnetic field. Okay, these will signify the direction of magnetic field. Now how to calculate the direction? Now for that again go to your thumb. Okay, then go to your thumb. Let us say come to the point A. At point A, since the cross symbol is given, that means the current is entering inside the plane. So put your thumb inside the plane of paper, and curl the finger. So once you curl the finger, the curling will be in the clockwise direction. Now, so these arrows, so these circles are to be drawn in the clockwise direction. Understood? Because here the rotation is towards clockwise, because the thumb is pointed inward, and once the thumb is pointed inward, if I fold my finger will curl towards the clockwise direction. Now, for the point B, if I place the thumb outward, means towards myself. So, if I fold the finger, in the finger direction will be anti-clockwise. Okay. So, these are the anti-clockwise loop that we are seeing. Okay. So, by this method, you can draw these lines or draw the directions. Okay. So, this is the nature of the magnetic. These are the lines of magnetic field. You cannot view it. You cannot see it. So similar to the electric field also cannot be visualized, but you have to feel it through experiment. So once you do this type of experiment, now you can get the idea of how the magnetic field are oriented. The magnetic field are oriented in a closed loop pattern. No, they are closed loop. So these are all circular types of loop and these are closed. So these are the variations. So if I go through this figure, so what you can see that current is flowing in this direction. That means through this point, the current is moving downward direction. Current is moving downward direction. Downward means cross. Okay. And from this point, the current is moving upward direction, means it is dot. Okay. So cross means if you put your thumb downward and curl the finger, so arrow will be in this direction. What is? Arrow will be in this direction. Now, if the cross symbol is there, so thumb is pointed downward, and if you fold my finger, so finger will be folded in this direction. So these are the different loops that you can see. All these loops are concentric circles. Concentric circles. But they are rotating in the clockwise direction. Clockwise circles. Okay. Similarly, here you can observe the anti-clockwise circles. These are the anti-clockwise direction circles. Okay. Understood. But there is one important point that these are the two different rotations. So if I say this is the one cross point, let us say this is a cross point and this is a dot point. Along the cross point, you can see different circles are there. Along the dot point, there are different circles are there. But there cannot be any kind of intersection. Okay, there cannot be any kind of intersection. Why? Because if the intersection takes place, that means the magnetic field are intersecting with each other. That is not possible. Okay, similar to the concept of electric field. So electric field lines cannot intersect with each other. Same as the logic goes over here also. They are existing as a closed loop pattern, but at the center, it might appear that they will intersect with each other, but they will not. Okay, they will not. At the center, the direction will be in this direction, but it is only one single arrow. Yeah, they are not intersecting. So regarding the direction, they will be either clockwise circle or they will be anti-clockwise circle, and they are concentric in nature because all are same center, circular shape, perfect circle. Yeah, perfect circle. And the direction is like this. Okay. So this is all about the how to check your direction. So whenever I switch on the circuit, whenever I allow the current to flow there, so magnetic field is being created and I have to plot this magnetic. Okay. I have to get the idea how the magnetic field is varying inside this. So I get that. Now, same magnetic field varies. So what we do this experiment? So we experiment for this experiment, what we do, we put the iron dust and we once switch on the iron, then you observe how the iron dust are oriented. Okay, that orientation of the iron dust will give you the idea about the magnetic field line. But the same magnetic field line can also visualize using a magnetic process. Okay, the same magnetic field line can be visualized using the magnetic needle also. Okay, so let us say there is a magnetic field line. So for the earlier field, let us say I am saying this is a wire, cross wire, through which if I draw the magnetic circles, so it should be clockwise. These are the magnetic field. Now if I place the magnetic needle, so magnetic needle will be directed in this direction. Always. Okay. So if I rotate the magnetic needle, so at different orientation, the needle will be pointed along the arrowhead direction. Arrowhead of what? Arrowhead of the clockwise direction. Okay. So that will guide you how the magnetic field is oriented. So pointer of the north pole will always show the deviation or the deflection along the magnetic. Okay. So by moving the magnet or the magnetic needle, you can get the idea about the which direction the magnetic field is there. Okay. So far we discussed about the two types of geometry. One is the circular coil and the current carrying. Now, so these wire or these loops are behaving as a producer of a magnetic field once you switch on the current. Okay, until and unless current is being there is no magnetic field being produced. Okay, That's why these are known as the electromagnet. Why? Because these magnets are operating only when we supply the electric current. These are known as electromagnet. Similar to the electromagnet, there is one called permanent magnet. So this is the permanent magnet. So for permanent magnet, the permanent north pole is there, south pole is there. So regarding the magnetic field line, for the north pole, all the magnetic field lines are emerging out from the north pole. Okay, all the magnetic field lines are emerging out from the north pole, and all the magnetic field lines are terminating in the south. Okay, so magnetic field lines are directed from north to south, outside the bar magnet, and all the field lines are closed here. Okay, so if I say this is the field line, this is the closed line. So if this field line is there, might be seen that it is discontinuous. No, it is not discontinuous. If I go on, so field will be connected like this. Similarly, this field line will be connected with the other field line like this. Okay, so all the field lines are connected with each other. Okay, outside the bar magnet, and inside the bar magnet, you have to make the curve to be closed one. So these lines are directed from south to north. Okay, these lines are directed from south to north. So these are the two different directions of the magnetic field line. One is from south to north and from north to south. Outside it is from north to south, inside it is from south to north. Okay. Now, how to plot that? So for that again, if you move the pointer or magnetic needle along this direction, so along this direction, along any direction, if you point it, so it will always show the deflection toward the north. Okay, so red colored pointer you can see it is directed along the arrow head direction. Okay, along this arrow, the red color pointer will mark you the direction. So you can plot this variation by placing magnetic needle about the magnet also. Okay, now come to the loop again. Okay, so this is the idea of the permanent magnet. Now we have discussed about this loop also. And for the loop geometry, how to find out the direction of the magnetic field? For the loop geometry, if you rotate the finger, along this current direction, thumb will give the direction of the magnetic field. So in this situation, the current is going along the blue arrow direction. If you hold your fingers along the blue direction, so thumb will be directed in the upward direction. Now, thumb will be directed towards the upward direction here. So what does it mean? It means that all the field lines are appeared to move away from this loop like this. Okay, these are the different magnetic field lines. Okay, so if you replace this loop by a permanent magnet, so what's the representation? So I can draw another permanent magnet for this. So what should be the direction then? It should be a permanent magnet above which the north pole will be there, and below it is south pole. Why? From the north pole the magnetic field lines are coming out. Now, that means this loop can be treated as a permanent magnet having north pole facing upward, south pole facing downward, because the loop lines, field lines are going inside. Okay. So every time if there is a coil, current carrying coil is there, you can visualize this coil by replacing it with a bar magnet. Okay. So bar magnet is an ideal example of a permanent magnet. Every time for the permanent magnet, you are going to use the bar magnet, or another type of magnet is a horseshoe magnet. Okay. Those are the categories of the permanent magnet. Rest are basically the electromagnetic. So both have some kind of utility. But one of the major difficulty or the major drawback of this permanent magnet is that I cannot change the magnetic field. What I have discussed that for the magnetic field strength to be changed, that can be allowed inside the electromagnet. Why? Because B is basically mu naught I by 2 R. This number. Okay. So in order to change this B, either you can increase the I, or I can say increase the N number also. With that increase in N number, you can change the B number. Okay. Then the magnetic field is controlled. Yeah, magnetic field can be controlled for the electromagnet setup. But that cannot be controlled for the permanent magnet. Yeah. For the permanent magnet, whatever the magnetic field is there, that is fixed. That is the strength of the magnet. That you cannot alter. Yeah, that you cannot alter. And the last geometry that you have to learn is called the solenoid. Okay. So far we learned about the two geometry. One is the straight wire, and the second one is the circular. Okay, circular. And the third geometry you have to understand is about the solenoid. And what is solenoid? Solenoid is a spring-like structure. Solenoid is a spring-like structure. So now, if I say this is the length of the solenoid L, okay, and this is the R, radius of the solenoid, Okay. Now regarding the solenoid, what we discuss about the solenoid which is known to be the ideal solenoid. What is ideal solenoid? Ideal solenoid are those for which the R number, that is the radius, is much less than the L. Let us say I am taking the R as 1 millimeter. Okay. And L is suppose 5 centimeter. Okay. Now compared to R, L is very large. So I can treat this as an ideal solenoid. Okay. So whenever I am saying solenoid, every time I am saying that it is an ideal solenoid. Now for this ideal solenoid, now solenoid cannot be placed in this manner. So for that, you put some kind of material inside. Okay, on that material you hold the wire. So that material placed inside the solenoid is known as a core. Okay, help of the core. So that core is made up of soft iron. Soft iron. The core is made up of soft iron. So once you switch on the circuit, if I allow the current to flow it, so then this solenoid will produce some kind of magnetic field. What is the magnetic field? So for that, we should define the magnetic field like this way: be inside the solenoid. Be inside, because solenoid can produce the magnetic field which is always exist inside the solenoid. That should be equals to mu naught into small n into what? Now what is small n? Earlier one, the n was the capital. Now we define another n, that's the small n. What is that small n? That is number of turns per unit length. Okay, length. Let us say how many turns are there? Let us say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let us say 15 turns. So capital N is 15. Nah? Let us. Okay, I might be wrong. Let us count it. Let us say I got 15 number of turns. So total number of turns is 15. And what is the length? Length is 5 centimeter. Now we define a small n number that is equal to 15 divided by 5 centimeter. But you cannot take it in centimeter. If you take it in meter, so multiply by 100. So it becomes 300. Okay, small n becomes 300. So what small n gives? The value of magnetic field within the solenoid. That means inside this solenoid, the magnetic field value is this. If I put one point, let us say the A point, A is outside the solenoid. What is the magnetic field at outside point? Outside point is always zero. Okay, the solenoid cannot produce any kind of magnetic field outside. Okay, it can only produce a magnetic field inside. And what is the number? That number is mu naught into n into 2. Remember that n number is small n. What is small n? That is number of turns per unit length. Now, regarding this expression, we can only use this expression whenever the solenoid is ideal. Okay. Now, for this ideal one, what is meaning is ideal one is that the magnetic field that is being produced by the solenoid is constant. Now, every number is constant. I am supplying a constant value of current. So mu naught is constant, so, and small n, depending on the number of turns given, so you can calculate the small n number. So that also is constant. That means it is a constant. Well, okay. Earlier, for the straight wire of the circular loop, I am getting the variable magnet. Okay. So for the straight wire or the circular coil, what I get the expression as dependency of each some other. So that means these are the variation. These are the variable magnetic field. But first one, this one is the constant. So whenever I am getting a constant magnetic field, it is known as the uniform magnetic field. Uniform magnetic field. Okay. So solenoid can produce an uniform magnetic field. That means its field remains constant throughout this. Regarding the direction, how to calculate the direction, I will show it. But first of all, understand that this is the first geometry that we are going to learn. Is basically a geometry which can produce the magnetic field which is of uniform in nature. Uniform means there is no variation. It remains constant. Okay. It remains constant. Now regarding the direction, what is the direction? Now let us say this is a kind of solenoid and this red dot implies the direction in which the current is being flowing. Direction in which the current is being flowing. If you hold your finger along the current direction, your thumb will be pointed towards B. Got it? You hold the finger along the current direction, in the right hand of the thumb will be pointed towards the B. Okay. And that B magnitude is constant throughout the solenoid. What is the value? That is mu naught into A into that number is constant. The number is never going to be changed. If you consider the outside point, B outside is 0. Okay, B outside is 0. Now there is another convention by which you can predict the direction. Let us say there is a coil through which you fold the wire, and let us say the coil is carrying the current, and once the observer is standing on the left hand side of the coil, let us say he sees the current is flowing along this direction, that means clockwise direction. Okay. From the left hand side, you are seeing that the clockwise current is entering inside the solenoid. Understood? From the left hand side, you are seeing the clockwise current. If you see the clockwise current from the left hand side, now place the finger along the clockwise direction, so thumb will be pointed towards this direction. No? So arrowhead is pointed towards this direction. That means that part of the solenoid is behaving as a north pole, that part is behaving as. Understood? So whenever you got the direction of the arrow, along the arrow direction, put the arrowhead tip, put the north pole opposite to the actual south pole. So that means this also can be behaved as a permanent magnet, in which this is the north pole, this is the south pole. So when the current is flowing in the clockwise direction. Okay. If you see the same current is flowing in the anti-clockwise direction from the left hand side. From the left hand side, now you are seeing the current is flowing in the anti-clockwise direction. If you fold your finger in the anti-clockwise direction, then the thumb will be pointed towards yourself. Now, for this situation, thumb will be pointed in this direction, so B will be in this direction. So for that situation, this is the north pole, this is the south pole. Okay. So if I see one direction clockwise from one side of the loop, then that will be anti-clockwise from the other side. Okay. So that's why you have to be very careful about in which direction the current is being flowing. Depending on that, you have to fold your finger, and accordingly you can get the correct answer. Okay, once you get the result, that means now you can visualize that this solenoid is behaving as a magnet. And what is that north pole and south pole? That you also have to understand. Okay, that also you have to understand. Let us say I am putting two solenoids. So these are the one solenoid. Let us say this is A solenoid, and this another solenoid B solenoid. Okay, B solenoid. Okay. Now from this side, you observe the current is flowing in the clockwise direction. Okay, and from this side, you are observing the current is flowing in the anti-clockwise direction. Okay, now clockwise current is flowing. That means for the B solenoid, if I see, so magnetic field is in this direction. Okay, if I say clockwise current, magnetic field will be pointed towards the thumb. For the anti-clockwise current, magnetic field will be pointed towards this direction for the second loop. Okay, now imagine the corresponding magnet over here. So for this A situation, this is the north pole, south pole. Why? Because the magnetic field lines are coming from the north pole. For the B magnet, again this is the north pole, from which the magnetic field lines are leaving out, the south pole. Now, instead of keeping two solenoids together, I can imagine that there are two magnets are placed side by side. Okay, so this is the equivalent system. So instead of saying that there are two solenoids are there, I can also say that the two magnets are. Okay. Now these two magnets will certainly repel each other. Why? Because these two north poles are coming towards each other. That means what you can finally conclude that they will repel. Yeah, they will repel. So this is the final conclusion that once you place two solenoids, depending on the direction in which the magnetic field are being produced, that can either repel or either attract. If I change the direction of the anti-clockwise current to clockwise current, then they will attract each other. Okay, so you can conclude whether they will attract, these two solenoids will attract, or these two solenoids will repel by only calculating the direction in which the magnetic field is existing. Understood? Now come to the dissimilarities between the current carrying solenoid and a bar magnet. Okay, so you know that the strength of the magnetic field due to a solenoid, that is equals to B, that should be equals to mu naught into small n into I, can be varied, can be changed by changing the current in it. So if I increase the current or decrease the current, then the B is going to be changed. That means I can change, but for the bar magnet you cannot change. whatever the magnetic field strength of the bar magnet is there, that you cannot change. Again, the direction can also be reversed. Okay. If I say for this solenoid, current is seen from the clockwise direction. Say from the clockwise direction, so magnetic field will be in this direction. If I replace the same solenoid by saying the current is being flowing in the anti-clockwise direction without changing the magnet. Here I am saying the current I is flowing. Here also I am saying the current I is flowing. Then the magnetic field line will be reversed. Okay. So without changing the magnitude of current, I can change the polarity. But for a bar magnet, if I see this is the bar magnet is there, if I identify this is the north pole and the south pole, I cannot change the position of the magnet. Okay. So bar magnet cannot be reversed. This is another advantage. So magnetic field can be changed, amount of magnetic field can be changed, and also the direction can also be changed. Okay.